1, 0. And they hit the bottom at the same time. But now, here I have a hollow one. You better believe it, that it's hollow. So now all the mass is at the circumference. And now it takes more time. Now the acceleration, as you will see, is half times g sine beta. In the other case, it was 2/3. And you may want to think about it tonight. Why this one takes more? It has to do, of course, with the moment of inertia. But again, it's independent of mass, radius, and length. So it's purely a matter of geometry. This one is going to be the loser. And this one, regardless of mass or length, is going to be the winner. You see them? One is hollow, one is not. This is very light, this is very heavy. I'll put the hollow one on your side. Three, 2, 1, 0. The hollow one lost and even fell on the floor. Yeah. I'm going to spin it with a high angular momentum, high spin angular momentum. And then I'm going to sit on this stool, and I'm going to torque exactly as you see on the picture on the right. I'm going to torque like this. And as long as I torque it like this, that spin angular momentum wants to go around in the horizontal plane. And when I torque the other way around, it will go back in the horizontal plane. I'm going to torque exactly as you see on the picture there. You ready? I stop the torque, nothing happens. I torque backwards, I keep torquing. I keep torquing, I feel it in my hand, I really have to push. I keep torquing, and I stop torquing, and it stops. So the angular momentum vector is chasing, so to speak, the torque. Is that non-intuitive? Very non-intuitive? It's also dangerous sometimes. We call this motion of the stool, and in this case the motion of the spinning wheel. Possible I gave it 3 hertz. But I will do what I can. I'll actually give it the maximum one that I can. That is always guaranteed success. Where's the wheel? The wheel is here. So we'll spin it up, and then we'll put it in here. Notice the way I'm spinning it. I'm holding it away from you now. I'm going to change it and do it differently next. And there it goes. About 10 seconds. Isn't that amazing? And it rotates seen from below clockwise. Now it's going this way, and I'm going to redo the experiment, changing the direction of rotation, and then it will go the other way around. So now the angular momentum, is it rotating like this, is pointing here. Spin angular momentum is pointing like this. Torque is like this. And so the spin angular momentum is chasing that torque. I'm the spin angular momentum, I'm the torque. This is the torque. It's chasing it. All right, so I had this in my right hand. That's all right. And now I will, so when I spin it, so let it first go around, which was roughly 10 seconds, what we calculated. And now I'm going to put 2 kilograms here at the end. And then you'll see an instantaneous increase in the precession frequency. You see, it goes much faster now. You take it off, and then it goes back to its roughly 10 seconds. So what I have done is I have increased this torque, but not at the expense of m. Because the reason why the m cancels is because... Let me show you the toy gyro first. Toy gyro. Oh yeah. Here's a toy gyro. Can you see it? Maybe I should make it a little darker here. Can you see my toy gyro? Yeah? I'm going to spin it, and then I'm going to hang it exactly the same way that that was hanging. I'm going to spin it for those who are sitting close, and then putting it horizontally and hanging it in a string. And you see exactly the same thing is happening. And now, through friction, of course, all this fun ultimately comes to a halt. I have something very special for you, or I may have something very special for you. It depends on my helper, who is here behind the scenes. I hear him, he's there. Great. Did you get full speed? I'm going to the airport and get a little tired and ask one of my friends to help me. Would you please help me and just carry this suitcase for me around, pick it up, walk around a little, make some turns. Turn the other way around, please. What the hell, eh? Yeah. Exactly. What are you doing, man? You're behaving so strangely. Make some more turns, man. We got to catch the plane. It doesn't quite do what you think it will be doing, right? So in here, you've guessed it.
Big spinning wheel or something.
Spinning wheel. And when you do this, you put a torque on it, and it does exactly what you least expect. It flips up. Isn't that fun? Yeah, you may get arrested when you go to Logan Airport with this suitcase. Thank you very much. It's great. In inertial guidance systems, you have a spinning wheel. At least in the days that the guidance systems had mechanical wheels. But that spinning wheel is mounted in such a way that you cannot put a torque on the axis of rotation of the spinning wheel. That's the way it's mounted. We call it three-axle gimbaled gyros. So the moment that you put a torque on it, the housings, in this case the yellow and the black housing, will start to rotate. And you never manage to get that torque on the spinning wheel. You never get it on this axis. And therefore, if now you put it on your boat or you put it in a plane, a missile for that matter, if you can never put a torque on the spinning wheel, and if the angular momentum for spin is in this direction, it will stay there forever and ever, assuming that we have no frictional losses. And if then the plane turns, the direction of the spin angular momentum will not change. But what will happen, of course, is that this yellow frame will rotate, or this black frame will rotate. And in these bearings here are shaft encoders. And they sense the rotation that the outer housing makes in order to keep this thing pointing at the same direction. And that signal is being fed back to the automatic pilot, and that keeps the plane flying in the direction that you want to. So you use as a reference all the time the spin angular momentum of your gyro, which is now mounted in such a way that you cannot put a torque on it even when the plane changes direction. And I want to show that to you. Uh-oh. Okay, this is the direction of my spin angular momentum. And I'm the airplane. And I'm going to fly. Look at that spin angular momentum. It has no respect for me. It stays in the same direction no matter how I fly. And the error signals that come from the bearings of the yellow housing and the black housing, those arrow signals are fed back to the automatic pilot, and so the plane will stay on course. Now what I can do for you to come to a final test on your thinking, this wheel is suspended in such a way that there is no gravitational torque on it, like there was here. But I can put a torque on it by simply putting some weights on the axis. And what do you think will happen now if I put some weight here on the axis? So the wheel is spinning, but now I'm going to put a torque on it here. It is spinning in this direction. Angular momentum is pointing straight at me, away from you. I'm going to put a torque on like this, putting the weight there. Torque will be in this direction. What will the spin angular momentum do? Torque is in this direction, spin angular momentum is in this direction. Spin angular momentum will start to chase the torque. Watch it. There it goes. The spin angular momentum is chasing the torque. You see exactly the same thing that I've shown you before. And if I make the torque higher, then the precession frequency will go up. See, it stops now immediately when I take it off. Put it back on again. Continues. Put more on it. Goes way faster. What happens now if I put the weight on this side? So I change the direction of the torque. If I put it on this side, torque is now in this direction. Spin angular momentum is in this direction. It's going to reverse direction. There we go. And you see it does. Amazingly non-intuitive. If you have problems with this, you're not alone. See you Wednesday.